viewers, this video is about power MOSFET. So power MOSFET is a type of MOSFET which is specially meant to handle high levels of power. These exhibit high switching speed and can work much better in comparison with the other low voltage level MOSFETs. However, its operating principle is similar to that of any other general MOSFET, and as operating principle is similar, so its transfer and output characteristics are also similar to a general MOSFET. Now, in this video, we will study about basics of power MOSFETs, then features of power MOSFETs, symbolic representation of power MOSFETs, structure of power MOSFET, and working principle of power MOSFET. And then lastly, we will study about the IV characteristics of power MOSFET. Again, to begin with, I will consider the fact that you all know a general MOSFET and its working principle very clearly. And then only I am proceeding with power MOSFET. Basics of power MOSFET. We all know that the full form of MOSFET is metal oxide semiconductor field effect transistor. Now, why metal oxide semiconductor? Because we know that a metallic layer is being insulated by an silicon dioxide layer. So metal oxide semiconductor field effect transistor. And these power MOSFETs have high switching frequency, which is up to 100 kilohertz, which is very much pretty good in consideration with the power electronics field. Now, we know that or we will see in the coming as we go on with the videos, we will see that the turn on and turn off characteristics is, or turn on time and turn off time is very small in case of power MOSFETs, because it lacks, or due to the absence of minority carrier. We all know that MOSFETs are majority carrier devices. So due to the absence of minority carriers, the turn on and turn off times are small. If turn on and turn off time is small, we will have a high switching frequency. Now, the third point worth remembering is, we know that BJT, power BJT, is a current control device. The collector current is dependent on the base current, and the base current is again dependent on the junction temperature. We all know as junction temperature increases, beta increases, which further increases our output current, that is the collector current. So there can be a false output in case of an power BJT, or an output which can go out of control. But it is not the case in case of a power MOSFET, which is a voltage controlled device. So as mentioned, the features of power MOSFET are low input current and also already mentioned voltage control device, which we can understand when we see the working principle of a power MOSFET. And it has high switching speed because the turn on and turn off time is low due to the absence of minority carriers. It is a majority carrier device. It is not a bipolar device. And they do not have problem of secondary breakdown, and has a high input impedance and is a active device. Herein is the symbolic representation of MOSFET or power MOSFET. which is of two types, N-channel and P-channel MOSFETs. We can see the N-channel symbol and P-channel symbol differs in the position or the direction of the arrows. And it has three terminals, the gate, drain and the source. And as mentioned previously, in case of power BJTs, power MOSFETs are usually preferred. N-type power, N-channel power MOSFETs are usually preferred because electrons have higher mobility in comparison to holes. This is the structure of power MOSFET. Again, this is a vertical structure, and the utilization or advantages of vertical structure I have already mentioned in case of power BJTs. Now here we see that we have a NPN structure wherein the N of the source and N of the drain are highly doped because you have a positive sign, and a body which is P, and in between there is a drift layer which is lightly doped N region. Here we are talking of an N structure of a N-channel power MOSFET. The gate is connected to the P-type body, whereas the source and drain are connected to the N plus or highly doped N-type semiconductor. The gate is insulated from the P-type through a silicon dioxide layer, as mentioned previously, which has a thickness of about say 1000 Armstrong, which is very less. And this silicon dioxide layer gives it the characteristics of a capacitor. Two conducting layers, in between we have a dielectric layer. The simplistic diagram or structure of the power MOSFET is shown in the right hand side diagram. This slide tells about the working principle of a power MOSFET. Here we have taken the simplistic diagram of the power MOSFET, and wherein the gate and the body is being connected with a battery which has a positive terminal connected to the gate. So if now we keep on increasing VGS, that is the voltage between the gate and the source, then a positive charges will be accumulated at the gate side. You can see here the positive charges being accumulated at the gate side. Now, due to the capacitive behavior of this terminal, we can have a negative charges being accumulated as shown in the diagram in between the two N plus layers. Or we can understand it in this fashion also. In the P-type layer, whenever you are giving VGS and keeping on increasing VGS, what will happen? The negative charges or the electrons will get attracted to the positive voltage and will be accumulated at the top layer of the P-type body. This forms the induced channel or the inversion layer, as commonly called, the induced channel or the inversion layer. So we can see we have a channel that is being formed between the N plus to N plus layers, which consist of all the electrons, because as N plus layer are highly doped layers, that means the number of electrons in those layers are higher. So we form a layer of or a path of electrons there. Now, when we provide a VDS voltage across the source and the drain, that is, we connect the drain and the source with a battery with a positive terminal connected to drain and a negative terminal connected to source. What will happen? The electrons will start flowing towards the drain. And as electrons flow, we know the direction of current is opposite to the flow of electrons. That is, we will have a ID flowing opposite to drain, that is from drain to source. This is our output current. Now, here we can see that VGS is controlling the induced channel or the inversion layer, which is controlling the flow of ID. So we call the MOSFET as a voltage controlled device. Here we can also we can say that the channel is formed in the p-type region. Similar to this, we can even have a P substrate or a P-type power MOSFET, provided we replace N-type materials with P-type and then reverse the polarities of the voltage applied. And already I've mentioned, although the structures of the normal MOSFETs and the power MOSFETs are seen to be different, the basic principle behind their working remains unaltered. That is, in both of them, the formation of conduction channel or the induction channel, whatever you call it, or the inversion layer is the same, which is nothing but the suitable bias applied at the gate terminal, resulting in the inversion layer. Further, it is to be noted that in case of power MOSFETs, which are based on vertical structure, the doping and the thickness of the epitaxial layer decide the voltage rating, while the channel width decides its current rating. The more the channel width, the more current it can handle, and more the doping, and if you alter the thickness of the epitaxial layer, the more voltage handling capacity the power MOSFET will be having. Now moving forward to the IV characteristics, this is the transfer characteristics of a power MOSFET, wherein we are plotting the input voltage VGS across the output current ID, keeping the output voltage VDS constant. So what we see, whenever we go on increasing VGS, at the first stage, the inversion layer starts forming. Then when we keep on increasing VGS up to a certain level, after that threshold voltage, the ID current starts flowing. So this is what is shown here. And the point from where the current starts flowing is called the threshold voltage. That is, for MOSFET to conduct current, the voltage VGS has to be increased up to a certain level. Before that, it will only help in forming the inversion layer. Now the output characteristics is same as the general MOSFET. Here what is happening, at a constant VGS, we are plotting the output voltage VDS across the output current ID. This is the output characteristics. As we go on increasing VDS, keeping VGS constant, ID will shoot up, that is increase instantly, and then will saturate at a certain level. But as we go on increasing VDS to a certain level, breakdown will occur, and avalanche, due to avalanche multiplication, ID current will shoot to a higher value. So here, when there was no conduction, it was called the cutoff region. And when ID starts increasing with a small change in VDS, it is called the ohmic region. And the region where ID doesn't increase with increase in VDS for a particular VGS is the active region. And the region where ID shoots to a higher value due to breakdown is called the breakdown region. So this is all about power BJT.